Welcome back to the School Science Shed. This is episode 3B in a series of videos which are aimed at helping you revise for your physics GCSE if you are studying in England. Now, physics is not different if it's in a different country. So if you're not in England, I hope this will be useful for you, but you do need to check your curriculum to make sure what you learn in this video is what you need to know for your course that you're studying. And really the same is true if you're in England as well. Do not use these videos as your only resource for revision, and make sure you check the syllabus to make sure you've revised everything that you need to. I've split this episode up. Originally I was going to do it as one episode, but I split it into 3A and to 3B. In 3A I looked at kinetic and potential energy calculations, and if you haven't watched it and you want to revise those, you can go back and do that when this is finished. In this video I'm going to look at important ideas in physics, which is the idea of work and the idea of power. So it covers calculations involving work and power. Let's make a start. So work is a really important idea in physics, and work is to do with transferring energy. So I don't know if you've really thought about this, but if you do think about it carefully, you'll see that whenever a force is moving, and it says here moving through a distance, I'm not quite sure what else it would move, but whenever a force is moved, energy is being transferred. So if we take an example of you pushing a table, you'll be using a force to push the table, and that will transfer energy from chemical energy from your breakfast to thermal energy because of friction between the bottom of the table and the floor. So we've got a force moving and we've got energy being transferred. The same would be true if you pushed a pram up a hill, but in this case you'd be transferring chemical energy to gravitational potential energy. Again, we've got a force moving and we're transferring energy. And then just a final example, if a lift is going up in a building, we have a situation where, yes, we've got a force moving because the lift is being pulled upwards, and what we've got here is energy being transferred from electrical energy, because there will be an electric motor that's lifting the lift. So it's electrical energy being transferred into gravitational potential energy. And whatever example you can come up with of a force moving, you'll realise that there is energy being transferred while that's happening. Here's another example just to really emphasise that. So if you stretch a spring, obviously you're using a force to pull the spring, and that force is moving, and you're transferring chemical energy into elastic potential energy. So how much energy is transferred? Well, the first thing I want to tell you, and it's not written down on this slide until the bottom, is that the amount of energy transferred is called the work. So that's what work means in physics. It means transferring energy from one form to another. And because work is about how much energy is transferred, it's measured in joules because it's an amount of energy, and energy is measured in joules. And how much energy is transferred, again, you probably would have guessed, it depends on how big the force is and how far the force moves. And what you need to do to find out the amount of energy that's transferred is you simply multiply the force times the distance moved. So work done is force times distance moved, and if we're writing that as letters, we're saying work is force times distance. So that's quite a lot to cover, isn't it? We've got this thing called work. Work happens when a force moves through a distance, and the work is the amount of energy that's transferred from one form to another, and we can calculate that by doing force times distance. So let's have a look at a calculation. A woman pushes a car 20 metres with a force of 300 newtons. How much work does it do? How much work, does she do? So if you watched the last video, you'll have seen that if we are doing a calculation, the first thing we do is a summary. So from the question, it says 20 metres is the distance. It doesn't actually say distance, does it? But again, if you know units, 20 metres is a distance. So that's what it is. It tells you the force is 300 newtons, and it asks you the work. So now we say, do we know a formula that's got work, force and distance in it? Yes, we do, because we've just done it on the last slide. Work is force times distance. We don't need to rearrange that formula because it's already telling us the work. So we just put the numbers in. Force is 300 newtons. Distance, 20 metres. Calculate the answer, 6,000 joules. Underline it so the examiner knows where our answer is. That's how you answer that question. There is a triangle to do with calculating work. And this can be useful if you're not very happy about changing the subject of an equation. I mean, don't tell your maths teacher. Your maths teacher will probably think you should be able to rearrange an equation without using a triangle, but it can be useful. If you've got an equation that's got 3 things in it, you can always use a triangle like this to change the subject to the equation. So the rule is cover the thing that you are trying to calculate. So if you're trying to calculate work, cover work, and what's left tells you the sum that you need to do. Work is force times distance. If we don't want work, if we want to find the force, suppose we know what the work is because the question tells us and we know the distance, but we need to find the force. We cover the force and what's left tells us the equation to do. Force equals work divided by distance. And similarly, distance, if we know the work and the force, but we want the distance, what formula do we use? Well, cover the thing you want, and what's left tells you the equation to do. So if you want to use that triangle, you need to learn it, and you need to remember how to actually use it for calculations. This is something that is important as well, and perhaps I should have mentioned before, but if a force is not moving, then work is not being done. So if we think about this little girl holding up the sign, I imagine that sign's quite heavy, and she's going to start to feel tired, and her muscles are going to begin to ache, but she's not doing any work because she's using a force to hold it up, but she's not moving that force. Everything is still, and work is not being done in this situation. So work is not done if the force doesn't move. Now let's move on. We've talked about work. Let's have a look at power. So what is power? Well, power is about how quickly energy is transferred from one form to another. And if energy is transferred quickly, that's a high power. And if energy is transferred slowly, that's low power. And that explains why a more powerful car, like this sports car here, has a much better performance. It will have a higher top speed and a better acceleration than this rather old and feeble-looking car here. So this car will go faster and it will accelerate better because it transfers energy from chemical energy in the petrol of its engine to kinetic energy. Whereas this one transfers energy slower, which will give it a lower top speed and also lower acceleration. So that's what power is. There's an equation for calculating power, and because power is about how quickly energy is transferred from one form to another, obviously if you're working out power, it's energy transferred divided by the time taken. You've got to make sure you get the units right. The unit for power is the watt, and the unit for energy is obviously the joule, and we need to use time in seconds. And I think the time is the one that will catch people out because there's lots of different units we can use for measuring time. We can use seconds, minutes, hours, days, months, weeks, whatever. But if we're going to be calculating power, we've got to use the time in seconds. And we've already seen, haven't we, in this video, that the energy transferred is also the work done. So this is the same equation. We just, instead of calling it energy transferred, we're calling it work done. And either of those is a correct equation. Now, there is a joke, and all physics teachers tell this joke. If your physics teacher hasn't told you the joke yet, they eventually will, or they're not a very good physics teacher. It's one or the other. Okay, so here's the question. What's the unit of power? And the answer is, that's correct. Now, It works a lot better if you just say it rather than having it printed on a screen. So let's just see why that works. Do you see? So if you say what, it could be a question, what is, as in what the question, or it could be a statement, as in the what is the unit of power. It's not supposed to be funny, so if you're not laughing, don't worry. Don't put it in the comments that the joke's not funny. I know the joke's not funny. It's all about helping you to remember the unit of power. So hopefully that terrible joke will help you to remember that the what is the unit of power. Let's have a look at a power calculation. So this is true. I've checked on Tesla's website. The power of a Tesla Model 3 is indeed 335 kilowatts. So how long will it take to transfer 7,500,000 joules? So first of all, we're going to do a summary. So let's have a look. Well, first of all, we've got the power, which is 335 kilowatts. But remember, in order for our formula to work, we need the power in watts. And this is in kilowatts. So I need to change from kilowatts into watts. So a kilowatt is 1,000 watts. So we need to multiply this by 1,000 to get it into watts. 335,000 watts. The energy is 7,500,000, and time is what we need to calculate. So we are asking, do we know an equation that has got power, energy and time in it? Because that's the information that's in the question. And the answer is yes, because we've just studied that. And this is the equation we know, but we need to rearrange it to make time the subject of the equation. Now, if you're good at maths, what you'll have done is you'll have looked at that and you'll have said, well, what I need to do is I need to get time on its own, and I certainly don't want it to be dividing. I don't want it to be the denominator. I want it to be on the top. So the first thing you would do is multiply both sides by t to get t times p equals e. And then you want to get p away from the t, so you divide both sides by p and you end up with t equals e over p. If you're not very good at rearranging equations, there is a triangle for power, which we will have a look at in a moment. So we've got our equation, t equals e over p. So now what we do is we put the numbers in. So E is 7.5 million, 7,500. P is 335,000. Put that on the bottom. When we work it out, we get an answer of 22.4 seconds. Underline it. Make sure we've got the unit. Calculation finished. Now I promised you the triangle, didn't I? Here it is. So energy on the top, power times time underneath. Cover the one you want. Energy is power times time because that's what's left. What if we want power? Cover power, energy divided by time. And what if we want time, which is what we were doing in the last calculation? Time equals energy divided by power. So you can use that triangle to find the right answer. So that takes us to the end of the second set of calculation of episode 3B. I hope it's been useful to you. If it has been useful, give it a thumbs up. If you've got any questions, put them in the comments. I've very much enjoyed explaining it all to you, and I'm looking forward to episode 4, which will be our next episode from the school science shed.